Hi, I'm Ming, and this is Kitchen Matters. We're a team of material science grad students helping you explore the science of food. Today, Ethan is joining us with a poultry predicament.
Thanks, Ming. So, the other day, I was trying to make fried chicken. However, I realized I was out of oil. So I decided to just fry my chicken in a pot of water instead. Because water is close enough. They're both liquids, right? But instead of turning crispy and brown like it usually does, I just ended up with this gray mess. I had the pot on the highest heat, just like I do when I fry chicken, so why didn't it turn brown?
To answer that question, we have to think about molecules. Just about all the food we eat is made up of tiny molecules. Take this glass of water, for example. If we could zoom in to the atomic level, we'd discover that this water is actually made of billions upon billions of water molecules. You are as big to a water molecule as the sun is to you. As you know, foods can exist as solids, liquids, or gases. In a solid, the molecules are held tightly together by strong bonds. In a liquid, the molecules are held less tightly together. And in a gas, the molecules have the weakest bonds between them and are whizzing around the container.
But water can go back and forth between being a solid, liquid, and a gas, right? How do materials change from one phase to another?
That's right. A substance can undergo phase transitions and convert from one phase to another. Let's take melting as an example. To melt an ice cube, we need to supply heat. As you heat up the ice, the molecules start vibrating with more energy, and eventually they have enough energy to break some of the bonds between them. Importantly, during these phase transitions, the molecules themselves remain unchanged. Liquid water is made of the very same molecules as the ice cube. However, it is the arrangement of those molecules that differs. Ice will generally melt at 0 degrees Celsius, and water will boil at 100 degrees Celsius. Different foods have different melting and boiling points depending on the arrangement of the molecules. Thinking about the material science tetrahedron, if there are stronger bonds that hold the molecules together, then the melting and boiling points will be higher, since you need to supply more heat to break those bonds. Water has a boiling point of 100 degrees Celsius, but many cooking oils have boiling points of 300 degrees Celsius because they have stronger bonds between the molecules. It's all well and good talking about these processes, but let's carry out an experiment to see for ourselves. We'll take a pot of ice and measure its temperature as we heat and melt the ice. We'll make a graph of the temperature over time. Initially, the ice is at -5 degrees Celsius when it just comes out of the freezer. As we heat the pot, we're supplying the ice with energy. The temperature of the ice slowly rises, as you would expect. Now here's a question for you. As we continue heating up the ice, how do you expect the shape of this graph to change? Which of these graphs do you think we'll find? Let's now go back to the experiment and find out. At this point, everything is still solid. We keep heating, and eventually we reach the melting point, 0 degrees Celsius. Now at the melting point, something quite curious happens. The temperature levels off, and it stays at 0 degrees Celsius.
Whoa, what's going on? Why did the temperature stop changing? Is your stove broken or something?
This is because once the temperature reaches 0 degrees, the ice starts to melt. During melting, all of the energy is being used to break the bonds between the molecules, and there's no energy left to increase the temperature. Initially, the sample is fully solid, but as time goes on and more bonds are broken, the ice is gradually converted to water. At the very end, enough bonds are broken so that all the ice has fully melted into water. Now the same thing happens all over again. The water continues heating until it reaches 100 degrees. Now the water starts boiling. And just like before, the temperature stays constant because all the energy is being used to break the bonds between the liquid molecules. There's no energy left to increase the temperature. Here's a question for you. Let's take these two pots of water which are both boiling. One pot is at high heat and the other is at low heat. Which pot of water is at a higher temperature? The one on high heat, the one on low heat, or are they both at the same temperature?
Surely the pot at high heat is at a higher temperature, right? I mean, that's the whole point of being on high heat.
Actually, both pots are at the same temperature. Let's think back to our experiment. When water is boiling, its temperature doesn't change. The pot on high heat might boil faster, but both will stay at 100 degrees Celsius throughout the entire boiling process. So even though it looks like one pot is boiling furiously and the other is only gently simmering, they're actually both at the same temperature, 100 degrees Celsius.
Okay, well that's really interesting and all, but let's get back to my original question. What does this have to do with my chicken?
The browning of chicken is caused by a chemical reaction called the Maillard reaction, which we'll discuss in a later video. And this reaction takes place at around 150 degrees Celsius. As we saw from our experiment, the highest temperature that water can reach is 100 degrees Celsius, because that's when water boils. Therefore, that piece of chicken will never reach 150 and it won't turn golden brown. On the other hand, cooking oil can reach 150 degrees Celsius because oil has a much higher boiling point, so it's still a liquid at that temperature.
Oh, so no matter how high I turn on the heat to my stove, the temperature of the water will never get above 100 Celsius.
So, what did we learn from this video? Solids, liquids, and gases are distinguished by the arrangement and energy of their molecules. During melting and boiling, we're breaking the bonds between the molecules, so the stronger those bonds, the more energy we'll need. Finally, temperature stays constant during a phase transition, which is why boiling pure water will never go above 100 degrees Celsius. In the next few videos, we'll explore how the reverse process of solidification happens, and we'll bring these concepts together to make chewy fudge and crunchy rock candy.